I think we should stop using this image. This has been used as a symbol for atoms for decades, but this likeness has been disproved since the 1920s. Now, before I explain all of that, here are the contents of this video lesson. Feel free to pause, replay, or skip parts of this video to make your study session more effective. Para sa aking mga kababayan, meron ding Filipino or Taglish version ng video lesson na ito sa YouTube, TikTok, Instagram, at Facebook. Kung mas komportable kayong mag-aral sa Filipino or Taglish, paki-check na lang ang account ko na Erico Fuentes. Alright, let's do this. Everything in the universe is made of atoms, and inside atoms, we find subatomic particles, protons, electrons, and neutrons. Now, among these three, the electrons are almost always involved in chemical processes, bonding, reactions, intermolecular forces. Electrons are almost always involved in these. Physicists have come up with many theories about the behavior of electrons in atoms. At one point, it was said that they are like raisins embedded in positively charged bread. Then it was discovered that the positive charges in the bread are concentrated only in the middle. And at one point, electrons were believed to orbit around the nucleus in the same way that planets orbit around the sun. But all of these atomic models were found to be inaccurate because physicists back then haven't considered the fact that electrons are quantum particles. Have you guys seen the Ant-Man movie by Marvel? The one with a superhero that can shrink using the Ant-Man suit? Ant-Man was warned by the maker of the suit to not overshrink to subatomic size, or to a size that's smaller than that of an atom. He was told that if he shrinks to subatomic levels, he will be brought to the quantum realm, a world where the rules of physics and science are a lot weirder than the world that we experience. Well, of course, the Ant-Man movie is a work of fiction, but their depiction of the quantum realm is definitely inspired by real concepts of quantum mechanics. But wait, what is quantum mechanics anyway? When we study physics, we learn about concepts like velocity, acceleration, forces, energy, and so on. And we apply these concepts to macroscopic objects, things that are not as small as atoms, and we can see them, touch them, and experience them in everyday life. The physics concepts that we learn for macroscopic objects fall under the study of classical mechanics. While classical mechanics is capable of describing the behavior of macroscopic objects, it doesn't do well in describing super small or super light objects like protons, electrons, neutrons, and small molecules. You see, the lighter objects they start to become more energy-like and less matter-like. And for these super light objects, the rules of the universe are a lot weirder for them, unlike the usual rules of physics that we experience. And that's what's being studied in quantum mechanics, the strange rules of the universe that apply to super small, super light particles which are more energy-like and less matter-like. This is the branch of physics that can help us understand protons, electrons, neutrons, atoms, and small molecules better. We are not going to study quantum mechanics in this video. Let's leave that to the physicists and chemists for now. There were many discoveries in quantum mechanics that helped us understand subatomic particles and the atom in general. But for now, we are going to focus on the development of the orbitals. Electrons, being quantum particles, have extremely unpredictable motion. It is impossible for physicists to know where they are and how fast they are going at any given point in time. And that is why the previous theories of electrons being like raisins in bread or like planets revolving around the sun are incorrect. But quantum physicists found a way to give us an idea on the possible locations where an electron might be. Using Erwin Schrödinger's wave equation, quantum physicists developed what we call atomic orbitals, or 3D maps of places where an electron can be found. For example, we have over here a d orbital. When we say that an electron is moving in a d orbital, we can imagine an electron moving in different directions and speeds, but it only roams inside this d orbital's space. The same can be said for other orbitals like this s orbital over here. S orbitals, as you can see, are sphere-shaped. When an electron is in an s orbital, we can imagine it to move in different directions and speeds, but it only roams inside this s orbital's space. The development of atomic orbitals has given us the most accurate depiction of atoms so far, the quantum mechanical model. In the quantum mechanical model, we still have the protons and neutrons somewhere in the middle of the atom or the nucleus. The electrons are outside the nucleus, moving around in random directions and speeds. But despite the randomness, we still have an idea of where the electrons can be, thanks to our orbitals, or the 3D maps of electron motion. Now, I understand that all of this might be a lot to take in since we are dealing with abstract concepts of quantum mechanics. These concepts might not be common to what we're studying in real life. So, if you feel the need to stop and take a break, please stop and take a break. It's harder to study with a tired body and a tired mind, so please take a breather if you need to. And of course, if you feel like you need guidance in studying chemistry lessons such as this one, please send me a message here or send me an email. I might be able to help. The calculations done by quantum physicists show that there are four orbital families or subshells. They are S, P, D, and F. These are the different 3D maps that can tell us where electrons may be. As you can see, each subshell or orbital family seems to have a distinct shape. Let's go over them one by one. The S subshell orbital is shaped like a sphere or like a ball. Unlike the other subshells, there is only one orbital in the S subshell, no other family members. The orbitals in P subshells are said to look like dumbbells because of the two lobes that each of them have. There are three orbitals in a P subshell: px, which lies along the x-axis, py, which lies along the y-axis, and pz, which lies along the z-axis. Meanwhile, here are the orbitals of the d subshell. Four of them look like clover leaves or double dumbbells. Then one of them, the dz squared orbital, looks like a dumbbell with two donuts around it. There are always five orbitals in the d subshell. Let's go over them one by one. The dxy orbital lies on the xy plane. The two other orbitals are named similarly. dyz lies on the yz plane. dxz lies on the xz plane. dx squared minus y squared also lies on the xy plane like dxy, but its lobes are aligned with the x and y axes. And lastly, we have dz squared, the dumbbell that lies on the z-axis. F subshell orbitals come in groups of 7. As you can see, they're rather complicated. We're not going to go through each one of these because 1, we won't be using them much in general chemistry, and 2, there's a lot of them and they're super complex. But anyway, you get the point. In these 7 f orbitals, we can find electrons in them too. Alright, let's do a recap of the things we have learned so far, specifically the terminology. Orbitals are 3D maps of an electron's whereabouts. They come in different shapes and sizes, and they were developed using concepts of quantum mechanics. Subshells are types or families of orbitals. The subshells we will study are the S, P, D, and F subshells. There are 7 orbitals in the F subshell, or the F family of orbitals. There are 5 orbitals in the D subshell, or the D family of orbitals. There are 3 orbitals in the D subshell, or D family of orbitals. And in the S subshell, there's only one orbital in it. No other family members. Now, let's talk about the electron capacity of orbitals and subshells. Here, we will be talking about the amount of electrons that orbital subshells can carry. Let's start with the S subshell. Here are our reference axes, and we shall imagine this to be the space occupied by an atom. Now, we know that the S subshells only have one orbital, this guy. On paper, we will be using a box or a blank for every orbital that we will be referring to. We only have one orbital here, so we will be using one box or one blank to symbolize it. Now, if an electron is found to be moving in an s orbital, we will use a half arrow pointing upwards as a symbol for that electron. We can notate this situation as S1 or an S with a superscript of 1. This means there is one electron moving in this S subshell. Now, what if there are two electrons found in this s orbital? We have already used an upward half arrow for the first electron. The symbol that we will use for this second electron over here is another half arrow, this time pointing downwards. Why downwards? Yeah, let's talk about this one first. You've tried playing with magnets, right? Bar magnets have north and south poles. Now, if we have two of them with the two north poles near each other and the two south poles near each other, we will see that this situation isn't stable and these two magnets will repel each other. To make these two magnets get along, we need to turn the other magnet upside down so their opposite poles will be near each other. Electrons, like magnets, have their own magnetic field. Just like the two bar magnets, two electrons would only get along in their orbital if their electric fields are oriented in opposite directions. This is called electron pairing, by the way, and this orbital contains what we call an electron pair. We'll go back to this concept when we study covalent bonding. Now, going back to our s orbital, this guy now has two electrons in it, so now we can notate it as s2 or an s with a superscript of 2. 2 electrons is actually the observed limit for orbitals, not just for s orbitals but also for p, d, and f. So at this point, this s orbital is full. Now let's have a look at p subshells. P subshells have three orbitals, px, py, and pz. Because of that, we will be using three boxes or blanks as symbols for these three p orbitals. The one on the left is for px, the one on the right is for py, and the one in the middle is for pz. If a single electron is found in a p subshell, it is observed to be moving in the px orbital. To notate this electron, we put a single half arrow pointing upwards on the left box, which is for the px orbital. We write this as p1, a single electron in a p subshell. Now, if there's a second electron found in this p subshell, in which orbital will it be found? Will it also be in px, the next orbital pz, or the farther orbital py? Well, according to the quantum physicist Frederick Hund, before putting a second electron in an orbital, all other orbitals in its subshell must first have one electron each. And that is why for sure we can't put it in px, since pz and py are still empty. The second electron instead will be found in pz, the next orbital. So now we put an upward half arrow on the center box. Now that we have two electrons in this p subshell, we notate this as p2. Now let's deal with the third electron. In accordance to Hund's rule, we need to put an electron to the empty py orbital before we put a second electron to px and pz. We notate this as p3, or 3 electrons in the p subshell. Now that our p subshell is half full, or all orbitals having 1 electron each, we can now put a second electron in each of these orbitals. So, for the fourth electron, we can now put it in px. We will use a downward half arrow now so that the magnetic field of these two electrons inside would get along. Notation, p4. The fifth electron, we can now put it in pz. We now have p5. And for the sixth electron, we can now put it in py. We now have p6. And with that, our p subshell is full. A p subshell with 3 orbitals, with each one capable of carrying 2 electrons, has a total capacity of 6 electrons. Now let's have a look at the capacity of d subshells. D subshells have 5 orbitals. Here are the 5 boxes and blanks labeled with the orbitals they refer to. The first electron in a d subshell will be found in the dx squared minus y squared orbital, or the leftmost box. We now have d1. Now, for the second electron, we have to keep in mind Hund's rule. We have to put the second electron in dxz, so now we have d2. And we will continue going from left to right. The third electron will be in dz squared, giving us d3. The fourth electron is in dyz, giving us d4. And the fifth will be in dxy, giving us d5. Now that our d subshell is half full, we can now put a second electron in each orbital. Electron number 6 will be in dx squared minus y squared, giving us d6. Then in dz squared to give us d8, dyz to give us d9, and lastly, dxy to give us d10. We now have a completely full d subshell. The subshells have 5 orbitals, each one capable of carrying 2 electrons. Therefore, the capacity of the d subshell is 10 electrons. We can do the same to f subshell electrons. F subshells have 7 electrons, and here is the box assignment for each of them. Now again, we won't be using f orbitals much in our study of general chemistry, but I hope you can try drawing the orbital diagrams for f orbitals in the same manner that we did a while ago. Please try practicing this on your own. So, how are we doing? Feel free to stop and take a break if you need to. Up next, we're going to talk about how subshells are arranged in atoms. We are going to use this orbital energy diagram that shows how orbital subshells are arranged in terms of their energy level. Found here at the bottom are the low energy subshells, and on top we have the high energy subshells. Now, if you notice, there are numbers written to the left of each subshell label. We call this the principal quantum number, or shell number, or simply the energy level of an orbital subshell. This one, for example, is an S subshell with energy level 1. This is an S subshell with energy level 2. This is a P subshell with energy level 3. And this is a D subshell with energy level 4. The energy level determines how fast electrons move in the subshells and how big their orbitals are. For instance, let's have a look at the 2s, 3s, and 4s subshells over here. The 3s orbital is bigger than the 2s, and the 4s is the biggest among them. This is because electrons at higher energy levels are more active or fast moving, making them occupy a larger space. And according to the off-bow principle of quantum mechanics, lower energy levels are the first ones to be occupied by electrons before the subshells with higher energy level. This means that the 1s subshell would be the first one to have electrons, followed by 2s, 2p, 3s, 3p, and so on. With all of those being said, let's try to apply everything we've learned so far, as well as the off-bow principle, to determine the arrangement of electrons in a carbon atom. Carbon has an atomic number of 6, meaning an atom of it has 6 electrons in its neutral state. Now, let's see which orbitals these 6 electrons would go to. The lowest energy subshell is 1s. Only 2 electrons can go in here, so we are going to put electrons 1 and 2 here. The notation for this subshell is 1s2, which means that there are 2 electrons in this 1s subshell. Right now, 2 electrons have been put in their orbitals. The next subshell is 2s. This is another s subshell which can only carry 2 electrons. So we will put electrons 3 and 4 in here. Our notation for this is 2s2, which means that there are 2 electrons in this 2s subshell. Previously, we have put 2 electrons in their orbitals plus 2 more in this current subshell, which means that we have put a total of 4 electrons in their orbitals. 4 down, 2 electrons to go. The next subshell is 2p. We can put 6 electrons here, right? But right now we only have 2 electrons left, which will only occupy the px and pz orbitals. We now notate this as 2p2, which means that there are 2 electrons in this 2p subshell. So this is how electrons are arranged in a neutral carbon atom. We now have an idea of where electrons are and how fast they are going because we know the subshells, orbitals, and energy level where each of them are roaming around. Oh, by the way, If we put together over here the shorthand notation of the subshells, we get what we call the electron configuration of this atom. While we're at it, let's go over the concept of valence electrons, or the electrons present in the subshells of the highest energy level. In the carbon atom, the subshells with highest energy are 2s and 2p because they're at energy level 2. This means that there are 4 valence electrons in a carbon atom. Writing electron configurations and determining the number of valence electrons are very important skills that we will use in studying chemical bonding and bonding theories. So please practice doing these. Let's try to do the same for calcium. Calcium has an atomic number of 20, which means that it has 20 electrons. Again, we will begin with the lowest energy subshell, which is 1s. This one over here. It can carry 2 electrons, so we will put 2 electrons over here. The notation is 1s2, 2 electrons down. The next subshell is 2s, which can also carry 2 electrons, so we put electrons 3 and 4 over here. Notation is 2s2. We previously put 2 electrons a while ago plus 2 new electrons here, and now we have a total of 4 electrons. 4 electrons down, 16 to go. The next subshell is 2p. We can completely fill up this subshell with all of its 6 electrons. The first one here on px, the next one on pz, the next one on py. And then electron number 4 here, 5, and 6. The notation is 2p6, and we added 6 new electrons, giving us a total of 10. 10 down, 10 more to go. The next subshell is 3s. We can put 2 electrons here. The notation is 3s2. We put 10 electrons a while ago and 2 new electrons now. And now we have a total of 12 electrons. 12 down, 8 to go. The next subshell is 3p, which can carry 6 electrons. We can put all 6 electrons over here. And the notation is 3p6. We added 6 new electrons, and now our total is at 18. 18 down, 2 to go. And those 2 electrons will go to our 4s subshell over here, which can fit in exactly 2 electrons. So we will put our 2 electrons here, giving us a notation of 4s2. Total, 20 electrons. Now the electron configuration of calcium is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. These are the subshells used along with their energy levels and how many electrons they contain in their orbitals. And while we're at it, let's determine the number of valence electron in this calcium atom. The highest energy level is 4, and only an s orbital is in this energy level. This 4s subshell carries 2 electrons, so we only have 2 valence electrons. And lastly, let's have a look at the arrangement of electrons in a bromine atom. Bromine has an atomic number of 35, which means it has 35 electrons. We begin again at 1s over here, which can carry 2 electrons. Notation 1s2. 2 electrons down, 33 to go. Next, we go to 2s, which can carry 2 electrons. Notation is 2s2. 4 electrons down, 31 to go. Next, we go to 2p, which can carry 6 electrons. So let's put all those 6 electrons in here. Notation 2p6. 10 electrons down, 25 to go. Next, we go to 3s, which can carry 2 electrons. Notation 3s2. 12 electrons down, 23 to go. We go to 3p, which can carry 6 electrons. Notation 3p6. 18 electrons down, 17 to go. We go to 4s, which can carry 2 electrons. Total of 20 electrons down, 15 to go. Then we go to our first d subshell over here, 3d, which can carry 10 electrons. So we can completely fill up this subshell with all of its 10 electrons, like so. Notation 3d10. As of now, we have 30 electrons in, 5 more to go. The next subshell is 4p, which can carry 6 electrons. However, we only have 5 electrons remaining in our electron count, so we will just put in 5 electrons in this subshell with this electron arrangement. Notation 4p5, giving us a total of 35 electrons. And now the electron configuration of Brahmin is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and 4p5. The valence electrons will be given by energy level 4, the highest energy level in this atom. There are 2 electrons in 4s and 5 electrons in 4p, which means that the number of valence electrons is 7. Alright, we're gonna stop here for now because we'll be needing time to process all of that and for you guys to practice writing electron configurations and determining valence electrons. Now, when you're done mastering all of these and you feel confident in your knowledge on the quantum mechanical model, I would suggest that you would try to study the shortcut to getting electron configurations using just a periodic table. In this method, you won't be needing the orbital energy diagram anymore. All you'll need is a periodic table, and you will be able to determine the electron configuration of an atom just by an atom's location on the periodic table. So please try to study that. Also, it would be nice to learn about the atoms that have exemptions to the off-bow principle. Some subshells have energy levels similar to each other, and that's why for some atoms, they don't follow the typical order of the subshells based on the orbital energy diagram. It's also important to learn about the electron configurations of ions. Cations, positively charged atoms, and anions, negatively charged atoms. I think we will cover that in our next video, so please stay tuned. It's also good to learn about quantum numbers, or the 4 numbers that give us the address or the state of an electron. We have learned about one of the quantum numbers already, the principal quantum number, which tells us the energy level. There are 3 other quantum numbers, and I would advise you to try to learn about them too. It would also be great to learn about the magnetic properties of atoms because this determines a lot of their properties as a bulk material. Whether they're paramagnetic or diamagnetic, it would be nice to learn about that too. And later on, you will be using your knowledge of the quantum mechanical model when you study chemical bonding, ionic bonding, and covalent bonding, and the different theories that explain these bonding types. If you get to study coordination chemistry or compounds made by the bonding of a ligand and a metal center using dative bonding, you will definitely be needing knowledge on the quantum mechanical model there. On the more practical side, you will also be needing your knowledge on the quantum mechanical model when you study spectroscopy, or the laboratory methods where we study the interaction of chemicals with light and different kinds of radiation. The type of interactions of atoms, electrons with radiation can tell us a lot about the properties of a material. So it would be nice to study this, and to do that, you need to brush up on your quantum mechanical model knowledge and skills. And if you need help in studying chemistry lessons such as this one, or lessons in physics, algebra, geometry, trigonometry, and statistics, and so on, just send me a message here. I might be able to help.